It's starting up.
All right. Okay, welcome back, everybody. I want to continue our discussion today of identification. We're going to focus mostly on linear dynamical systems, but I want to show you how broadly applicable that is. All right, so just for context, this is the second of two approaches that we're talking about so far for sort of system identification. The first one we talked about was the multi-body parameter estimation, where we took the original equations of motion of our robots, noticed that if we didn't write the full forward dynamics, if we avoided inverting the mass matrix and we kept it in the inverse dynamics form, then those equations turns out to be linear in the lumped parameters, right? So that it's the parameters we tend to want to identify, mass, length, friction, stuff like this, can be separated in a fine way from the nonlinearities like sine theta and other of the sort of trigonometric nonlinearities that we might want to deal with that might otherwise complicate our analysis. So leveraging that really important separation, we were able to do least squares estimation basically to identify the identifiable lumped parameters, right? It's possible that not all of the parameters of your robot are identifiable from data, like the inertia of the bottom link of a robot arm is typically only identifiable along one axis, right? But even more subtle things happen. But that's a super powerful recipe to be able to take and leverage least squares for a very nonlinear system identification. There were a bunch of important topics that came up to there, and we'll see them rear their head again. We talked about equation error versus simulation error, and we talked about this notion of needing parametrically exciting trajectories. In the parameter estimation case, we even gave a simple algorithm where you tried to optimize the condition number of your data matrix and try to find trajectories that basically somehow stimulated all the parameters so that you could identify them. Okay, and then the power of that, I think, is it's tempting to say that that's only limited to if you know the model perfectly, but actually that approach goes pretty far if you start putting other residual dynamics terms, any sort of nonlinear basis functions that are with linear combinations of nonlinear basis functions can be added right to your multi-body equations, and that can work very, very well. Okay. The one big limitation that I want to make sure is clear is that this is the case where we have the parameterization. It might be a generic parameterization from the nonlinear basis functions, but we still have some parameterization of the dynamics here. And in particular, the one that I think eventually runs out of steam is assuming that you have a state representation, right? So that you even know what size the vector x is. And in the examples I like to give of like buttoning my shirt or whatever, I don't know that I even know what the state of my shirt should be because it's technically infinite dimensional. How do I make a small approximation that's good for control? So that's the biggest reason that I think we need to look beyond multi-body parameter estimation and think more generally of the system identification problem, where you're given input-output data and try to discover a state representation, even for very hard problems. Okay, now there's one more sort of pillar. So a lot of that is like ongoing research. People are writing papers all the time right now about this kind of topic. But just like I think multi-body parameter estimation is one of the sort of pillars of background knowledge that you should know if you're going to do work in that area, there's another pillar of work, which is understanding how to do identification for linear dynamical systems, which does address this problem of having to discover the state representation in pretty sophisticated ways, right? Of course, everything's easier when it's linear, but my goal for today, to some extent, and I think it'll take maybe a little bit more of notes and maybe even a future lecture to fully hammer that home. But well, I want to at least get started. So let's consider the more general problem of fitting a problem that is, in this linear dynamical system form, potentially input-output, although we'll start with the state version. Okay, and in particular, the X variables may not be known until identification. You're just given a bunch of U and Y data, and you maybe have to discover X. This is not only good if your system is linear, but we've seen the power of LQR and linearizations and the like for nonlinear systems. So I'll try to make that point today too, that I think that's a big part of what I'll make today, is that you can actually use this for nonlinear systems to describe local performance of a nonlinear system. And I think you might actually be surprised that some of the work that we've seen recently actually is sort of doing this, okay? And I just said how important it is to discover state representations from input-output data. Okay, so let me start with some of the basic, simplest case ideas here. So remember I talked about, moved the iPad and warped to the end, okay. So we talked about equation error versus simulation error. Right, so what was the difference between equation error and simulation error? The simulation error, right, was talking about if I were to take I have two models. I have the model I'm trying to estimate, and I have the true model of the system that I've got data from, right? In the simulation error, you try to set them at some initial conditions and just simulate them both forward independently and ask how well do those long-term simulations stay, how close do they stay together, right? And that's a very robust metric for, if you can simulate, basically open loop your system and get the same answer as the real system, that's a very strong notion of identification. But it tends to be very hard because, even the pendulum I talk about, you can't simulate, you can't do, complex closed form solutions in time of even very simple mechanical systems. So in practice, what we end up doing is just looking at the one-step error, where for every data point, if we have a trajectory of data, in the case where we have state, for instance, we will basically say, given this state, this action, one step ahead, how close is my model to my data? And then I will reset basically reset the model to my data on the next step and take one step and just accumulate the one-step costs, right? So if we're going to start, let's start in the case of where we know the state space. So I'm using the whiteboard that I don't like as much. I know the writing isn't as clean, but I'm using that because I am going to make use of the slides.com videos in a little bit. So yeah, I hope it's okay. Okay, so assume we have data in the form UN and XN. So I'm not going to solve the state discovery problem, if you will, in the first step. Okay, so I typically call the data U0 or UK. So I'll use a subscript notation when I'm talking about the actual value that I got in some data set. Okay, and I want to fit a linear model. So the one-step error, the equation error, gives a sort of the simple optimization problem that you would sort of expect, okay? And the way that we're going to write that, and the way that people almost always write this in the system ID world, is they start building these block matrices and these big data matrices, just like we did in the multi-body parameter estimation. Okay, so let's make a big data matrix X, I'll call it big X, where I've got X0, which is a vector, X1, X2, all the way through to, let's say, X capital N. Actually, let me truncate it a little bit. I'll do X to N minus 2 here. Because let me also write X prime as a second vector, which is the same thing, but shifted by 1. Okay, and I'll write my U, my big U data matrix in the same way, carrying around the proper shifts. So I'll go up to N minus 2 again. Okay, then it turns out if I want to fit this model, AX plus BU, then you can write that just as a big matrix expression, where I want to basically say my big X prime, which is just the shifted by 1, should be approximately equal to A matrix, B matrix. This is blocked together into one big matrix, times another block matrix, where I've stacked X and U together. I wrote this notation of saying X prime is approximately equal. I'm hating what the whiteboard's doing to the legibility of my writing here, but I hope that's clear. X prime is just AX plus BU. That's just a big block matrix multiplication. Okay, and it describes the dynamics if it was perfect. And what I've written this, approximately equal to here, because what I want to do is just solve a least squares problem. To estimate A and B. Okay, so you should really see this as basically like a linear least squares, AX equals B. Okay, this time I have A here, X approximately equals B. That would be the way I would normally write it. Okay, so the things that ironically, the thing that I'm calling A and B is my X in this problem, right? But this would be the standard least squares. Okay, so so it should just be least squares. Okay, now let's put it to work. I cooked up an example to try to make it sort of stick how this would potentially work in practice. And I think it actually, I was very happy that I did it because it revealed a bunch of the subtleties that happen when you get into the details of this. Okay, so the recipe basically is the basic recipe is very simple. The details get complicated. So what I want to talk about here, I'm sorry, but if you flip back to the Zoom screen now, let me show you a little bit in a Colab notebook. Okay, so here's the setup. I want to take a cart pole that I don't know very well. I've made a spitball guess at the parameters of the cart pole, just enough to build a basic LQR controller based on a rough model. Okay, so the cart pole, I can put it at the top. I got the mass, the length wrong, so it's kind of not a very good controller. Okay, but it's just enough for me to start getting data. Okay, and then what I'd like to do is use the data generated by running this not very good control while it's hanging out around the top to fit a linear model, and then use that linear model to design an LQR controller, replace it, and get back the controller that would be basically as good as if I used the true parameters. Okay, but this time I'm not fitting the multi-body parameters. I'm just fitting a linear model directly to the data. Is that setup clear? Yeah. Okay, so a bunch of code here. Most of it is copied over from the original LQR balancing controller. Okay, I just said the upright state of my cart pole is, of course, is that upright. I've got my balancing LQR. Minor difference, because I were talking about discrete time, I used the discrete time multi-body plant. So you'll see that the time step is set to 0.1, which is a relatively big time step, but it's fine for this system. Okay, and then I've got an argument whether I want to change the parameters. If I do change the parameters, then the URDF had some initial parameters. I completely butchered them. Like I went from 10 to 6, from 1 to 1.5 kilograms, right? I left the length the same, but I figure you should have a ruler. You can get the right length right. Okay. And I set those parameters, okay? And then I'm going to log the output to get my data. And roughly, I'll ignore some of these details for a minute here. Roughly, I'm going to simulate it 15 times, grab the data from the log, and put it into my my data frame, okay? And that's all that's happening here. But let's just first see that it has the effect I want. So if I run the cart pole 15 times and plot the left plot here is the X position of the cart, the Y is the theta position of the pole, okay? So if I use the original parameters and the original LQR, then I'm in a regime of initial conditions where things deviate, but they all kind of stabilize nicely to the origin, okay? If I change the parameters to my other one and use the LQR controller for the designed for the wrong parameters, so the actual cart and pole haven't changed, only the model I used to design the controller, okay? Then I execute that controller. As I said, it really wasn't hard at all to find controllers that, I could change the parameters a lot and they would all hang out near the top. The cart pole isn't that very hard of a optimization. So even if your model is very wrong, you can still get a controller that hangs out near the top. Okay, but it doesn't converge nicely to the top. So this is kind of moving around the top. Now there's one other thing I did, this input excitation equals true. I'll come back to that in a second. Okay, so now let's run linear system identification on the data that use the wrong controller. Okay, so most of this is just unpacking my data frame. I tried to use pandas data frames, in order to, and into my big data matrices. And then really, it is really just a call to linear least squares on these block matrices. And then I have to pull apart A and B from the matrices. Okay, things look good here. The least squares rank is 5. So the A matrix should be 4 by 4, and the B matrix is 1. So by the time I invert it, I actually want a rank 5 solution of this big messy system, and I have relatively low residuals. But that, I guess, shouldn't convince you yet. Let me just show you that. Did that run? Unrecognized, nice. Why would it suddenly decide that it doesn't recognize the kernel? Well, I think that means I have to pay the startup cost again. That sucks. Well, maybe not. Let's see. I'm still deciding if I like this collab on the iPad as a way to present. I'm sure it's giving you guys a headache when I'm spinning up and down. I apologize. What the heck? doesn't like something I did here. Well, when you run it yourself, I promise that the A and B are going to come out like right on the right numbers. And I guess what I can't convey very easily in the demo here or whatever is that it was actually super hard, not hard, but just it took a lot of, I got it wrong a bunch of times before I got it right. Okay, so there were a lot of details to get right to make these A and B matrices come out the right way. Okay, and the system stabilizes beautifully with the learned model. Okay, so one of the things that goes wrong, which maybe I won't try to run just now, but one of the things that goes wrong is if you only run the controller with the LQR controller with no extra excitation to your parameters, then in fact, when it says least squares rank out of possible 5, you always get a 4. You don't get a full rank solution. And if you think about it, it's very natural because by virtue of running a controller that is a linear function of your state, U is always going to be linearly perfectly correlated with your X's. Okay, so if you only run your LQR controller and just watch your LQR controller, then you've actually haven't fully excited your dynamics. So it took even adding sort of random noise to it tends to be a bad idea because it gets filtered out by the dynamics. So in practice, this input excitation that I added is just adding a slow sine wave, anything that's uncorrelated, and it's relatively small. Anything to make the inputs slightly uncorrelated from X is enough to bring in the extra sort of richness, excitation richness to the data. Okay, and once I got that, boom, everything fits perfectly to the A and B matrices that come out almost numerically perfect, and the controller worked well. Without that, when you have a low rank solution, A and B just didn't happen to match the true A and B, and the ways that they didn't happen to match in this sort of low rank solution made the resulting LQR controller garbage. Okay, so I do think there's a lot of lessons hidden in there, and I hope you'll try it later, and I'll make sure that it runs on Colab. I'm not sure what happened there. Any questions about that? Right, it's a pretty reasonable model. You've got a system, you've got a rough model for it, just enough to get it operating. And then but it's enough to put it in the regime where your linear model could be good. And then you can do stabilization, right? It would be hard to stabilize the upright without that initial controller, right? You wouldn't get enough data near the top. It'd be really annoying to get data near the top, right? If you had just open loop trajectories or something, you'd have to reset it a bunch of times, and you could eventually get some data there. You'd be fitting, fitting a model, but from much less data. So a very standard thing to do is to find some stabilizing controller to begin with and generate data with that stabilizing controller. So we actually, the original cart pole in a Jupyter notebook is sort of not the, the amazing thing that you'd like to be able to do with a method like this. Here's one that's a little bit more fun. Okay, we actually took a cart pole and took the pole and made it into a wing, okay, and put it in a water tunnel. And so now the dynamics are the state space is basically the cart pole state space plus the state of the fluid, which is incredibly complicated, infinite dimensional, Navier-Stokes stuff. Okay, and it's going to be operating in a very nonlinear regime. Okay, but the context is sort of similar to what you could do with a cart pole. So if you think about this is actually it's a cart. I'll show you pictures of it and videos of it in a second here, but imagine this cart pole, but it's turned on its side, okay? And it's put in a water tunnel with water flowing as the blue arrows indicate here. Okay, the wing is this red thing. It is an airfoil. It could be a flat plate. We have a couple versions. You'll see a couple on the different videos. A couple different versions of it, but the aerodynamic center of a proper wing or even a half plate is somewhere in the middle of the wing, right? It tends to be quarter chord for a reasonable airfoil. Okay, so that means the aerodynamic center is in the left picture, fairly close to the bottom. The pin joint is the black dot, which is where the thing rolls around. So just like the cart pole tends to fall down due to gravity, this one will weather vane around and want to rest at the bottom, right? That's its stable solution, is that the system's going to go into this weather vane to that side, and the air will be pushing it this way, and it'll be in this left solution. Okay. The goal, again, the stabilization at the top equivalent here would be to go to the far right, which is to have the system up this, and it's in an unstable equilibrium in this case. But the unstable equilibrium is given by the fluid dynamics now, right? So the dynamics of that airfoil are not somehow just sine and cosine, it's the fluid dynamics. And in particular, if you look in the middle, that's just a cartoon of as soon as you get into slight angles, you can get very, very complicated fluid dynamics going over the wing, okay? And especially when you've stalled the wing, okay? And this is actually, I think it's a nice example of we did this at a time when we were thinking a lot about the birds and how birds are flying, and it was a follow-on for some of the perching work, and we were thinking about what would it take to have very aggressive maneuvers from an airplane or a bird or something like this. In particular, you'll see we're going to do some cases where the fluid dynamics are very complicated. So if there's a gust of wind, is it true that a bird can actually change directions more quickly than in a gust of wind than a fixed wing aircraft? Okay, so this is kind of a setup that I'm going to build up for you to try to convince you that there's some cool stuff to do there. Okay, so this is a case where I don't have a parametric model, right? The multi-body parameters that I would write for a cart pole are not representative of the full dynamics of the system, because the full dynamics are governed by the fluid body interactions, which are very hard to model. We did make some fluid dynamics models of it. They're very computationally expensive, and they were not very accurate for our physical setup, but that was probably because our physical setup wasn't a little ghetto. But it was you'll see, there's a lot of hot glue and stuff. So this was actually work by John Roberts. It's in his thesis. If people want to look up later, there's a reference. John was great. Okay, so this is the physical setup. Okay, so, and it's actually, I hope you'll see that it's a video. So on the right is the pole. It's actually balancing in this video. And then when we turn off the controller at the end there, it weather vanes around and goes to the bottom. This big wheel you see at the top is an inertial wheel that we put on just so we could calibrate, we could change the inertia without having to change the airfoil all the time. And it tends to be useful to have a more massive wing, so you don't get just totally battered around by the fluid dynamics. Okay, and if you can kind of see that this is you could see some hot glue already in this experiment here, but this is sort of looking into the side of a water tunnel where the water is flowing from left to right in that video. Okay, so maybe I'll play it one more time here just so you see the same thing, right? So the cart pole goes up and down in the video. The track of the cart is sort of up and down, and the pole weather vanes around, and that's falling down. Yeah? Got the basic setup? Okay. So the first thing we did, we took our first principles model, and in this case, it was a flat plate model because in that particular wing is a flat plate. Okay, so you could take that first principles model and build an LQR controller, and it kind of works, but it's actually pretty similar to what I just showed you with the cart pole system, right? It was good enough to keep it up, but it never really stabilized, and it was very low performing, poorly performing controller. Okay, so then we did almost the same recipe here, but we did it experimentally. We just ran that controller a bunch of times, collected a bunch of data of we have encoders and the like on on the carpole system, the hydrodynamic carpole system. And we tried to fit the model, the linear model, around the upright. I'm sorry, I didn't make that one autoplay, but if you hit play on that one, and the performance becomes very good. It's never perfect, actually, because for some subtle reasons in the fluid dynamics, it's very hard to be perfect. And again, our water tunnel is not a perfect water tunnel. This was something we built from scratch ourselves in CSAIL. Okay. The interesting thing, though, is what more you can do with that. So already we just did something we have never done before in this class. We took a system that I don't have any equations for, and we stabilized it with LQR. Right, that's pretty cool. But this is a snapshot of a bigger idea, which is this idea of iterative learning control. I'd say it's a precursor of RL. This has been around for a long time. I think reinforcement learning has built on a bunch of results from iterative learning control. And this is sort of the model-based version of that, where I built a model. I tried to design my new controller based on that learned model, and you could imagine just iterating, right? So now I've got a better controller. I can get some data on that, fit a new model, repeat. That gets even more powerful if you switch to sort of a time varying case. So let me just sort of step through that. You can see that okay.
Oh, could I ask a question about the water tunnel?
Totally, yeah.
I was just curious, like I was a little surprised that collecting data from running the LQR controller was like parametrically exciting enough for the linear model to wind up being so good.
Yeah, so awesome question, because I had just emphasized that. So here's what happens, right? Is that so I think we probably did add some noise to you also, but also the water tunnel did us a favor, I guess, by giving us sufficiently rich trajectories, if you will, right? So sometimes the system can be noisy enough in ways that it'll excite the dynamics.
Also, what was the yellow thing on the other side of the water tunnel?
You're going to see what that is. That's the second part of the story. Yeah, there's a leading vehicle that may or may not shoot vortices at the cart pole.
Okay.
Okay, so you can imagine doing exactly the same thing. And maybe I won't write too much here since my whiteboard solution's stinking it up today here, but you know, we talked about time varying linearizations, right? So if you looked at if you thought about, just think through what you would do to formulate the same sort of, if you collected data along a trajectory, X and U pairs, and wanted to fit time varying A and B, there's really no difference. I mean, you have to build slightly different data matrices, but the recipe still works. Of course, you might need more data, more trajectories potentially to get sufficiently rich for you're fitting a lot more parameters, right? You're fitting independently parameters A for time 0, time 1, time 2, time 3. But the basic recipe of doing that with least squares is completely intact. Okay, now think about what you're doing right now with your problem set, doing iterative LQR as a means to doing trajectory optimization. Okay, so if I do this plus iterative time varying LQR for trajectory optimization. then this recipe, if we can, there's a big if, but this recipe has the potential to allow us to do trajectory optimization in an iterative learning control way on a system where we don't have the model, right? Where we only get the model from data. Okay, so on the hydrodynamic carpool, I'm going to show you how this works. Roughly, we have an aggressive maneuver that we want to make. The one thing that the hydrodynamic carpool does have going for it, and most of these systems do have going for it, a lot of fluid dynamics experiments have going for it, is that they're relatively repeatable. There's a lot of work that goes into building a water tunnel, so it's repeatable. So if I run the same controller a bunch of times, it might not accomplish my task, but it stays in a relatively modest tube around the set of solutions. Okay, so if I execute some open loop trajectory with some parameter excitation around it, okay, a bunch of times, and I can build a local linear model from the data, then I'm in business, okay? Because I can then take that local linear model, fit a cost function that may not have its minimum at the current trajectory, right? You can do trajectory optimization, take the quadratic approximation of some cost function, like balancing, update my nominal trajectory, update my LQR controller, now run it a bunch of times again around this new trajectory, wash, rinse, and repeat. And suddenly we've gained the ability potentially to do trajectory optimization for systems where we don't have a model. And that played out nicely in the hydrodynamic carpool example. Okay, so we ultimately, the original idea was that we would swing up from the bottom, right? But it turns out that that was a pretty messy thing to do, partly because the airfoil we needed to be so wide that it would barely fit in the tunnel and all these sort of things. But you could do something that is relatively relevant for like an aircraft, right? Which would be, I mean, if you're in the plane, if you're a 2D aircraft, then all you can sort of do in terms of evasive maneuvers is sort of, you can change elevation very quickly, for instance. So this would be the carpool hanging out at some initial condition and up at the balancing fixed point, and want to do a very fast change of let's say elevation for the aircraft. Okay, so this is a transition between two stable fixed points. We know how to stabilize either fixed point with the first controller we learned, but that trajectory, that transition between the two, it involves more nonlinear dynamics, time varying dynamics that we don't have closed form solutions for. Okay, so you can take the LTI model that you do and try to track the step, and it just did its maneuver there. It sort of works, but man, just like the other thing, it was enough for us to get data, but it was pretty messy. Okay, there does another track like this. You know, it overshot it a little bit, it swept and stuff. It did make the transition, it didn't fall down. It was enough to generate data, but it wasn't a great controller. And then if you use, you can do step tracking after you do a couple rounds of this sort of time varying linear dynamics. And we got a much tighter controller, much faster convergence and much, faster transition and faster convergence to the new fixed point. Okay, and John has loads of data showing that sort of how that plays out. But the basic story, I hope, is kind of clear. Here's maybe the simplest version of that data, right? So the balancing controller, if you just change the set point, it does eventually settle, but it just goes slowly there. The initial guess of the feed forward trajectory using designed, assuming that the model was time invariant linear, was the red, and after some iterative learning control, we get this green. Pretty big improvement. Okay, enter the leading vehicle. Okay, so if you watch closely on this, that fin in the front is designed to basically shoot vortices at my plane. And this is actually, let me tell you quickly that one of the big questions I had when I was studying the birds, everybody talks about how, how a wing should allow you to be more agile in the air than a fixed wing. Like a bird's articulated wing should be more, versatile. They also talk about incredible flow sensing with like leading edge feathers and the like. You can actually watch during high angles of attack that feathers will actually cause separation, and there's receptors at the wing tip insertion on the wings that actually sense the vibration that might be correspond with flutter and the like. So there's a sense that birds could actually sense a lot of the nonlinear dynamics while it's happening. Okay, but I said, wait a second. If you wait until the vortex or whatever gust of wind hits your wing, then it's basically too late, right? So it's almost too late to respond. And I think a lot of people agree with that. But we don't really have a great answer. So if birds, we've seen videos, I'm sure you've seen them too, videos of like, there's my favorite one is there's some experimentalists, standing on the top of a ridge with their parkas like flapping in the wind or whatever, and they take their little eagle friend with cameras on his back and they let him go, and he just soars up, and his fingers are doing their thing, his tail's doing its thing, his head is rock solid because he's looking for a mouse 200 feet below. So the gusts of wind on a ridge are just ridiculously complicated and fast moving and the like, and that bird is holding his head perfectly still, and it's just playing with the air and looking for a mouse. So how the heck does that happen, right? So if a bird can't, we know that there's some amount of time it takes for if you change even the angle of attack of your wing, it takes some amount of time to get a response, so to get a change in your lift. There's like an aerodynamic time constant that people understand to be, measured in sort of in the aerodynamic time constant is the amount of air that it takes the air to go from the front of your wing to the back of your wing. And it takes like a big fraction of that or more or multiple of those constants. So if you wait until a gust of wind hits your leading edge, it should be too late, I think, to do a recovery. So I don't actually know the answer to this. I started asking all my biologist friends, like, what happens there? I heard some crazy things like maybe birds are actually watching particles of dust in the air and they're actually doing flow measurement. Yeah, I don't know. I mean, probably when leaves are blowing on the ground or something, they probably get more out of that than I do, but I don't really know how they do it. Maybe they've just learned really good models and they can expect these things coming. But this experiment was designed to scratch that itch for me and for John. We started saying, what would the performance of even a controller we know how to write do if it was given a disturbance like a gust of wind or a vortex that was hitting it, and even given the ability to sense that vortex before it hits the wing versus when it hits the wing. The optimal controller in a setup like this where we can actually optimize, can we understand the trade-off in information of waiting till the vortex hits the wing? Okay, so that was, sorry for the long-winded, but this is one of my favorite experiments to try to dig into that. So the thing you see on the left is roughly this, it's actually played back in this MATLAB animation on the right, which is real data being played, animated, just in a cartoon form, so you can see what's happening. Of course, we actually estimate the location of the vortex in real time and track it. And it basically, you want to see that again, but it knocks the cart pole is balancing on the bottom here. The leading edge, the leading wing turns, send a vortex, knocks the cart, and it gets perturbed pretty significantly and returns to a stabilization. Fluid dynamics are awesome, right? So this is a flow visualization of that release. We actually built this whole setup where we were doing real-time flow visualization. That was a new thing back then. People had always been doing flow visualization offline because it was so computationally intensive, but we teamed up with some experts in FPGA that were trying to do it in real time, so we could close some control loops with it. And this is what it looks like in the sort of camera's view of the vortex being sent down towards the wing. Okay, so if you can track the vortex, can you do better with the control? All right, so this is the particle setup, is that we have the cart and the pole, like you see. The hidden things that you can't see is that we actually are shooting a laser into the side of the water tunnel. We're seeding the fluid with particles, those you saw in the last videos there. And then we're taking a picture of those particles from above, and that's how it lights up and makes the videos I just showed you. Okay, and then we're taking that camera view, sending it to some FPGA to process and do particle image velocimetry and estimate vortices, and then send it back and try to give it to the controller. That's all just because it's fun. Okay, that's the laser illuminating relatively badly. This is like, for any real fluid dynamicist, they would tell me this was incredibly messy, but this was our first attempt at experimental fluid dynamics in our group. Okay, and this is roughly the story, is that if you build a controller now where you include the state of the vortex in the state of the controller, and then you use this iterative learning control to fit a better linear model and a better LQR controller that uses now the state of the vortex plus the state of the system, then we can take this original example where the airplane, if you will, the hydrodynamic carpool, is massively perturbed by a vortex. And we can change it into a setting where the controller responds preemptively to the vortex in order to minimize its effect. So in this case, you see that the red was the original, the pink was the informed one that knew the vortex was coming. And just to play that again here, so they're doing basically the same thing up to the data, right? And then the pink one knew it was coming and went and lined itself up and took that vortex exactly where it wanted to, just when it was starting to come back up again, so that it minimized. There was two versions of this. One of them tried to minimize the total deviation of the pole. The other one had its weight on the total horizontal deviation that was caused, trying to minimize that. So I think that's what this one is. So the dark red is the original LQR controller, the pink is the informed one, and it just got out of the way. That's actually pretty smart, right? It's just kind of like, let that one go by, I don't need that. And that's how you minimize the horizontal deviation. So for those of you that don't care about birds, I'm sorry for the distraction, but let me ask if there's any questions about that.
Can you play that second video again?
Yeah. So the pink again is the smart one, the informed one. It just kind of moved out of the way. You know, sometimes the optimization will just make you realize there's kind of an obvious solution that you just didn't think of. But it's good. It's good when that happens. I was hoping somebody would ask me, what's the answer to the question, right? And I didn't actually tell you the answer, which is, how early do you need to know where the vortex is? So we did this experiment, right, where we basically did the same kind of setup, but we hid the vortex for longer and longer. So it'd be like you could see it right when it was about to hit you, or you could see it a little bit further. You basically put a blinder over the camera for the first part. And you could ask the question, how does the performance degrade if you do this? You know, we're in the land of approximate optimal control, but it is optimizing and doing a pretty good job of getting an optimal controller. So you have to qualify our statement with the fact that it's not necessarily guaranteed to be optimal. But for an optimizing controller, there was a characteristic point, which if you waited and didn't see the vortex until it was like roughly halfway in the middle of the screen here, if there was a point where the performance was good, and then if you blinded it until just a short time before it hit the wing, the controller of the informed controller was unable to do better than the uninformed controller, right? So the information did seem, in this super simplified, contrived setup did suggest that you needed to know before they hit the wing in order to do well, right? So I'm still stuck. I don't know how birds do it.
Does controller knows like how strong the vertex is, or does it only knows where it is?
So it knows where it is, but we do our best to provide consistent perturbations. So we have another motor that's doing the little flip to try to send a consistent vortex.
I see.
You could imagine trying to do more, right? Trying to estimate more of the properties of the vortex. Yeah, we did try to estimate roughly its center, its velocity, its radius, but the center and the velocity were the most reliable tracking that we had at the time. The other lesson of this that I love, I mean, so first of all, I learned a bunch of lessons about experimental fluid dynamics in there, including there were a couple days. There was one day where I took a walk of shame, having been playing on the water tunnel and screwed up a hose and basically sprayed 200 gallons a minute worth of fluid at my face, roughly. And then I had to walk across Sea Sail to the restroom to clean up. And you know, like every professor I knew and every student I knew walked by at that time and said, "Oh, why are you soaking wet?" Right? And so I had to explain that I just shot myself in the face with a water cannon. And John, my student working with me at the time, he's a funny guy, and he just let me have it. He tore into me about that every day until he shot himself in the face with 200 gallons a minute worth of water, and then we were even, and all was well. But also, like, it's just, MIT is a great place to be, right? I borrowed that laser, right? I walked down the hall and found some of our friends that do fluid mechanics, and someone's basically like, "Yeah, you know, don't shoot your eye out, kid, you know, but we can get you started on experimental fluid dynamics," right? So that's a pretty powerful laser, right? So I love the attitude and the support that you can get around here. Okay, so back to more robot-y things, although that's definitely robot-y. So you might not realize that actually the same recipe has been powering a lot of the kind of things we see in RL. So this is, I'm sorry, I didn't autoplay it again. This is Sergey Levine's work on contact-rich manipulation skills. The paper emphasized the guided policy search, but see the linear Gaussian control training. In fact, when they're doing this work, this part of the story, the impressive parts of the videos here, were actually, as far as I can tell from talking to Sergey and reading the papers, very similar to the story I just told you about in the hydrodynamic carpool, where this system was executing trajectories repeatedly, fitting local linear models, linear Gaussian models, and then doing effectively iterative LQR to iterative LQG in order to improve the controller. Okay, and it just worked incredibly well. Like, I was so impressed the first time I saw these videos. Those were tasks that I would have thought were very, very hard. Again, I think one of the biggest keys to success for something like this is that the experiments can be relatively repeatable, right? So you need to be able to generate multiple trajectories that's sort of on the same, in the vicinity of the same solution in order to fit a reasonable local model. But if you can do that, you know, sky's the limit. Right, so this is without explicit modeling of all the contact forces and contact mechanics that we've been talking about. Right, so if you look at the abstract, I mean, a lot of it is about the guided policy search, which is a different part of the idea that I can tell you about later in the class. But the approach learns a set of trajectories for the desired motion skill by using iteratively refitted time-varying linear models, right? That is, the recipe is very, very similar. It's interesting to watch that group continued the work, and they were spent more time thinking about iterative LQG or its alternatives. And my understanding is that the favorite version of iterative LQG for those experiments these days is this BADM, Bregman alternating ADMM, Bregman ADMM. So, and it appears as BADM in their papers. So, do you expect that to? Are you surprised that that works? I mean, should we expect that local linear models can describe contact mechanics? We've been talking about non-smoothness of contact mechanics a lot, right? But we've also talked about ways to take gradients through contact, right? So even if when we've done even the hybrid trajectory optimization through contact, right? That is a perfectly good way to take a gradient, a linearization of the system around a trajectory that makes and breaks contact, right? And if you could do that with finite differences, if you have small enough perturbations, that you'd expect that same matrix to come out from finite differences, right? So those gradients, I think people often say that non-smoothness, that contacts can cause lack of gradients, and that is often, I think I emphasized in the video you watched, that's not necessarily the case. You can take gradients through contact, and you can fit local linear models through contact. When you start and stop making contact completely, you should expect a discontinuity, right? So right, if I have trajectories that are in contact and I move my system a little bit, but I'm just making a contact at a slightly different place, a slightly different time, then I'd expect smoothness there in the solutions. Local linear models could fit well. If I get to the point where I'm really like barely making, some of my trajectories are making contact and bouncing off, and some of them are missing contact and just continuing on, that would be a place where I'd expect local linear models to not perform well. So you would hope that some sort of, that it would still fit a model, and you'd hope that it wouldn't be a fixed point of your optimization, right? That it somehow you'd power through that messy spot and get to another good solution. But
is that what the paper was doing? Because they must have run. Is that what?
Say it again.
Is that what the paper was doing with powering through? Because they must have run into cases where it's like they must have run into discontinuities with the tasks in the video, right?
Yeah, I think the work probably deserved more attention on the part that I would consider, I consider super interesting, and Sergey might consider boring, that the refinement of the local trajectory optimization part. I didn't see enough data to know exactly what's happening there, but yeah, I guess that's what has to happen, is that they must be just powering through it, right? And I don't think I mean, that's a likely place to have local minima. So sometimes you can get around that maybe by putting extra terms in your cost function to help power through that, or other things like this could help, right? Could make something like that work. Those are the parts that I don't know. Okay, so you guys have energy for the output version of it? Let me at least start that part, and maybe it's going to get the details might take longer, but I think it's a super important thing to understand. Okay, so and I have been working on putting the notes in. The notes are coming as fast as I can for this part. This is a new part. All right, so let's say we want to fit models now of the form xn+1 then yn is cxn plus du. Okay, there's even extra things to do if you have noise, noisy measurements or process dynamics noise. But in the case where, actually, if you just think about fitting this model directly, just by leaning on the power of least squares, you actually get some, there's some statements you can make about the solution being good, even despite you have white noise, basically. It tends to be that you can do better if you take a, basically use a Kalman filter type approach, then you can do even better. But let me just sort of set the problem up here, okay? So just like we've done before, where we start building our data matrices, we're going to build data matrices for this problem as well. This time, our data comes in the form of just y, k, uk, but not xk. Okay, and our goal would be to discover x. Now, almost all of these methods, you pick the size of x and then try to fit x, the best x given that size. And even I should be careful saying the best x, because there are many x's that could solve the problem equally well. So just picking an x that optimizes the objective. Okay, but for instance, in a problem like this, where you just have u and y, if I found some x that's very good, right, and I just reorder the indices of x, right, that would be a different representation in x. Clearly, if I reorder all the A and B matrices appropriately too, clearly it can describe the input-output data just as well, right? And in fact, any similarity transform, any invertible transform of the matrix X could potentially describe the data just as well. Okay, so finding some X is the statement, not finding, I have to be careful about saying the optimal X. Okay, we form our data matrices. And this time they're going to be even bigger in some sense. I'm going to take y0, y1, y2 across here, just like I did in the original state-based, but I'm actually going to repeat them again in this Hankel matrix form. Okay, so just ym in this case, and then that's going to go all the way down to some n minus m. So I'm going to repeat them. A Hankel matrix, right, is one that just has this striped form. I have A, B, B, C, 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 D, D, like this. This is a Hankel matrix. And I get that here just by construction. I'm going to set up all my data in this way, and then I'm going to shift it by one, shift it by one, shift it by one. And that's why I've picked this another constant capital M to go through, so that I have enough data to shift it all down and have many copies of the data. Okay, and then I'm going to do the same thing, or well, something similar with U. I'm going to write U0, U1, I guess it is the same thing. I can. Now the X matrix, my X state is going to be the same state sequence I did before, but this time it's unknown, so I have to come up with this. Okay, but here's the big trick that makes things kind of work out. So if I roll out the dynamics, then I can start seeing the important structure, right? So y0 looks like this. If I were to write y1, I can actually write that in terms of x0 u0 and u1. And in general, yn is going to be a complicated, or not that complicated, but it's going to be a stereotyped function of x0 in all of my u's. Don't need to write that down or anything, that's in the notes, but okay, that's a form. You've probably seen similar versions of that rolled out linear system before. Okay, but the key thing here is that y at some future time is a linear, a complicated, there's a bunch of matrices involved, but matrix multiplications involved, but it's a linear function, of course, even in the long term, of the initial conditions and the u's. So if I have my u and my y matrices here, I can actually, in this block form, write this in a big block matrix form, that y block matrix is some big matrix times a u plus some smaller matrix, it tends to be called gamma, times my x data matrix. Now again, I don't know x yet. This would be true if I knew x, but I have to discover even x0. So here's the magic, right? With some mild assumptions, basically that the data in your U matrix is not overlapping. It has a different column space than the data in your X matrix, which actually is roughly what goes wrong, what went wrong in my LQR example that I started with. But as long as U, the data in U and the data in X span different spaces, then I can actually find H, I can find the X and I can find gamma without knowing A, B, C, and D, okay? So the amazing result, I guess, from your data. And then you can also find gamma this way. And after having done that key step, you can go through and with clever applications of singular value decomposition and like, you can back out A, B, C, and D. In particular, in order to choose a good A, B, C, and D that is sort of well-formed, there's a whole notion of choosing, you do a weighted singular value decomposition to get a balanced truncation, a balanced realization. So that's a story that I feel like I don't have enough time to give you the full details of today, but I will make available in the notes. And if there's time, I'll make another spot and lecture for it, because I think it's really important conceptual idea for what makes a good state space. I feel like oftentimes we're trying to do roughly this, and we're running into some of the problems like balancing coordinates and the like without even realizing it when we're trying to apply these things for nonlinear systems. And I just want for you to feel like you can always go back and think about it clearly in the linear systems case, right? And of course, my goal, your goal probably is to do this for nonlinear systems, but I really think there's some important lessons to be found here. Okay, but least squares, singular value decomposition, some important projections, an oblique projection, they're all the stuff of, basically the stuff of linear algebra, can take a big data matrix in Y and U and kick out a good state X, and then A, B, C, and D matrices that will describe its evolution just from input-output data. Okay. Now, the way that you would use this, you might not know how many states your system even has, right? But you can ask, what is your reconstruction error of this sort of least squares problem that you set up? And basically, you could start saying, well, how well does the system describe the data if I have X of dimension 3? Or what about 4? What about 5, right? And you'd expect to get better and better fits until at some point where you have diminishing returns given the size of your state vector. And that's the kind of way you would try to find a good state representation for your system. And those states aren't going to necessarily look like theta 1, theta 2, or they're going to be some complicated function of that would be a mixture of variables, even if you applied them to a multi-body system. Okay, but they are discovered purely from data. These are the latent states, I guess, if you will, in the machine learning version of it, right? That would be your latent state representation. So that's just a teaser for that part, but hopefully it at least helps you understand where I think that literature falls in the importance. Any questions or comments or thoughts about that? I'll drop in some numerical examples in the notes for sure. Okay, so that's 2 out of 3 big approaches, I would say, to system identification. The third one, of course, is deep learning these days, where there are a number of important variants. I think the answer somehow, I think, requires knowing all 3. And I don't know if anybody's really got it yet, but I think this is the fringe of where we can really understand how to do great control from things that we don't have simple models for yet. So please let us know if there's any lecture notes, examples, or anything that I can add to help with your projects. I love the questions that have been coming in. Any other feedback you might have. And I'm happy to hang out for the last few minutes and answer any questions people have.